Good afternoon, everybody. Hope you can hear me all right. Or actually, good morning, rather. Like we said, my name is Ian Cummings, and I'm going to be introducing to you technology today called Assess, which we believe has applications in non-destructive testing in the aerospace industry. So in 2016, SpaceX lost a Falcon 9 rocket when a composite overwrapped pressure vessel, or COPV, exploded on that rocket. And that COPV exploded because there was a small hidden defect that went undetected in that COPV. When we assessed the total cost of that loss, it was about $350 million, not even counting the damage done to the launch pad. And thinking more broadly about the impacts of that failure, the satellite that was on that rocket that was going to be launched was intended to provide internet access in Africa. So the aerospace industry really has a strong need for advanced ultrasonic NDT techniques that can detect these kinds of failures and prevent these kinds of catastrophes. Looking at the aerospace industry as a whole, we can see that in recent years, the launch cadence for the aerospace industry has rapidly increased. Focusing specifically again on the Falcon 9, we can see that a large part of that increase has been dominated by the ability for SpaceX to reuse previously launched vehicles. Thinking about the broader space launch industry, there are now 49 private launch providers. Some of them are developing rockets, some of them have rockets that have been launched. Last year alone, there were $14.6 billion invested into launch vehicle development. Shifting kind of over to the to the broad non-destructive testing market in the United States, that was evaluated at $3.4 billion in value in 2020 with a projected growth rate of over 7.7% over the next 7 years. All of this is to say that the aerospace and NDT markets are growing, and there's room for new technologies and new solutions to the hard problems that they're facing. If we think about the traditional aerospace launch paradigm, it has been to build your rocket, transport it in parts to the launch site, assemble it, test it, launch your rocket, and then anything that's not intended to stay in orbit gets destroyed or remains in orbit. But the new reusable launch vehicle paradigm has closed that loop by landing or recovering components from the launch vehicle, disassembling them, refurbishing them, and then cycling back through that launch loop. The problem is that there are many opportunities for damage in this whole cycle, which means that there are many areas where you might need to actually inspect the rocket or components of that rocket before you use it again. And the whole business case that makes these reusable rockets financially viable is based on the ability to close this loop quickly. So to this point, the fastest launch-to-launch closed loop that SpaceX has been able to achieve is 27.2 days, but they'd really like to be able to do it in 24 hours. And we believe that inspection is going to be a large component in that loop closure time. And so for that reason, we think the aerospace industry really needs faster ultrasonic NDT techniques. If we consider some of the existing competitors or existing solutions, you have something like this ultrasonic testing crawler, which is a small robot that can be driven along a surface or crawl along a surface and inspect a small area with a contact ultrasonic probe, or perhaps a phased array probe. These solutions are typically too slow. They're really only applicable to simple structures, and they require a lot of manual input and control from an NDT technician. On the other hand, you have a more advanced solution like laser ultrasonic testing, which excites a structure with a high-powered laser and measures the response with a low-powered laser and repeats that point by point as it scans across the surface. The problem is that these solutions, though faster than ultrasonic testing crawlers, are still too slow for the aerospace market, and they're very expensive. A single system can cost on the order of several $1 million. They're also very sensitive to the surface finish of the test article in terms of their signal-to-noise ratio, and they're not very portable, which means they're not well suited to agile launch environments. We believe that the Assess technology is a strong answer to many of these problems. We inspect structures by exciting them with an ultrasonic transducer or several transducers attached to the structure with a single ultrasonic tone and scanning a laser Doppler vibrometer across the surface of that structure. This is a low-powered laser, and it allows us to capture a wave field image of how the waves propagate through the structure and interact with potential defects. taking that wave field image, we can do some additional processing to generate detections or regions of concern for a potential NDT inspector. Our technology is relatively mature at a TRL of 5 for many applications, where we've done a great deal of laboratory and some field testing. We've been awarded several patents and have several more in the pipe, and we have several copyrights on our software and are planning on copywriting some of our latest developments in the near future. Our vision for the ASSESS technology is to make launch cadences faster via rapid, large area inspection. Again, our system is 1 to 2 orders of magnitude faster than the competing ultrasonic inspection solutions. We can scan much bigger regions because we're only using that low power laser. And that also means that our system is eye safe inherently. So with the laser ultrasonic testing solution, you would have to build interlocked scanning areas and use PPE. That's not required with our solution. We're also capable of scanning real 3D structures and doing analysis over those structures, and we're working on advancing that part of our capability. In the past, we've demonstrated that our solution can inspect composites, metals, and additively manufactured parts, and all of these materials are common on the launch vehicles that we see today. If we take a quick look at the competitive landscape for our technology, the mouse system, the automated C-scan inspection system, and the PAR systems, laser ultrasonic testing system. The big key point here is that our system is much, much faster than these competitors, and that's really the driving factor in adoptability in the reusable launch vehicle market. If we think about the markets that we want to approach with our technology and where we might have a good fit, we believe, again, that the space launch industry is our beachhead market. And we believe that because they have a need for the technology today, and they have the regulatory freedom to pursue new inspection solutions immediately. From there, we think we could break into the government aerospace market, working with folks, some of you who might be on the call in the Air Force, the Space Force, and NASA. From there, we believe that the biggest eventual market for our technology would be commercial airlines. If you think about it, every airline that flies is itself a reusable launch vehicle, just not in the same sense as a rocket. The problem with this market is that there's a large regulatory barrier to entry, so your technology and your business model have to be very mature to be able to overcome that regulatory barrier. So how do we get technology into the hands of our first customers? Well, we here at the laboratory are good at developing this technology, but we need to partner with a commercialization firm, someone who's experienced at taking ultrasonic technologies and driving them to market. And we would license our technology and analysis techniques to them, and then work with them to have them sell hardware, software systems, and scanning as a service to our initial space launch customers. So where's our technology at and where are we going? Well, for several years, we've been able to detect composite impact damage, hidden metal corrosion, and even cracking in metals. And we consider that kind of our first minimum viable product. Currently, we're working on developing and improving our automated structure extraction and analysis techniques, and we kind of consider that MVP number 2. We're also working on in situ as-built detection and analysis for additively manufactured parts as they're being built. And we have a development effort for detecting the kinds of defects in COPVs that caused the failure of that Falcon 9 rocket in 2016. As we move forward, we hope to integrate these technologies and techniques to allow us to inspect aerospace structures and materials. And really, that's the next step for us. What we're looking for is a partnership with an aerospace launch firm that would allow us to get hands-on with their structures so that we could increase the readiness of our technology to scan these kinds of systems, detect the kinds of defects they're interested in the materials and structures that they're concerned about. And with that, I'd like to thank you for your time. My name is Ian Cummings, and I'm excited to answer your question.
Great, thanks, Ian. Over to our panel. Do we have any questions? Go ahead, Matthias.
Thank you. So thank you, Ian, for the presentation. I have a question. I understand your inspection system based on laser technology is 1 or 2 orders of magnitude faster than any other inspection types that are out there. What about the quality? Is it as good as the current gold standards are? do you have specificity and sensitivity numbers available already?
Right. So we don't have sensitivity and specificity numbers. There are applications where our technology would be better suited than the existing technologies and vice versa. So our technology relies on exciting what are called guided LAM wave modes. So we typically operate in thin plate-like structures. They don't have to be flat, but something like a sheet of metal or a sheet of composite, something like that. And we're generally detecting defects on the order of several centimeters in size for a large defect, down to something several millimeters in size, perhaps, or smaller for something on an additively manufactured part. That's kind of the gist of where we're at with this technology. We will probably not be the technology that you do the hyper precise imaging with, but we will be the technology that allows you to do the inspection across the surface of a large area, and then allow you to then zero in with maybe perhaps a more precise technique. But the idea is that the existing techniques simply can't operate at the speeds that we need to be able to inspect these large structures. The other nice thing about our technology is that we can trade scan speed for the precision of our measurements, and we can do that kind of cleanly in a continuous fashion.
But then, if I may, a follow-up question. I understand you were saying in certain areas your methodology might be even better than the slow gold standards, and in some areas of applications the slow gold standards are still required. Does this not mean at the end no time is saved at all, because for certain steps the slow gold standards are still required?
That's not necessarily true, right? So it might be enough to get a general indication of a defect without being able to precisely image that defect and say exactly where the defect is. It might be enough to say this is a region of concern, and then look at this much smaller region with a slower technique, which does in the end still save you time.
Okay, thank you.
Thank you.
Go ahead,
Yeah,
John.
thank you for the presentation. Good to see you again. You've taken this a long way from when we first started it. So what do you want to do with the technology? Do you want to do a startup? Do you want to create a strategic partnership with someone? What is, in your eyes, what's the best step forward for you and the technology?
Right, yeah, I think the best step forward for us and the technology would be to create a strategic partnership or an R&D partnership with an aerospace firm, really, again, to give us that opportunity to get hands-on with real structures, right? It's one thing to do testing in a lab. It's quite another thing to be able to demonstrate your technology in the field and to get real data on structures that people are really concerned about.
Are you working on that actively right now?
We are talking to potential partners and kind of exploring that space.
Thank you.
And time for about one more quick question. Any additional questions from our panel?
Thank you, Ian. This was really interesting. Maybe it's more of a continuation of Matthias' question, but so I understand that what you do is a first pass, a large scan, and then you zero in on where you identify defects. So it's kind of a two-step process. But for the first step, is this fully holistic, or do you have to, are you looking at every possible material? Can you look at every form factor that's required? So does your solution cover all the needs for your customers for that first step of a large scan?
Sure. So I think I should step back and clarify that not every application will require a second scan. There are a number of applications where this technology would be enough and is precise enough to show the extent of the defect well enough for someone to kind of make to probably take that and make a go, no go decision. So just to set that out there, right. The second point is, are we capable of scanning all the sorts of form factors and materials all at once? That depends on the materials. So this technology is better suited to those that transmit energy better. So we're well suited to things like metals and composites, things of that nature. Additional materials beyond that or specific structure types would perhaps require some more R&D. Like I said, we're still kind of in the midst of developing our analysis techniques that allow us to analyze the waves that are coming off of, or that we're measuring on real structures. But we've demonstrated some of that technique so far. Does that answer your question?
Yeah, thank you.
Thank you.
Great, thank you, Ian. Thank you to our panel and thank you to our other presenters during this session. We're gonna have a short break now, just a couple of minutes, and we will return shortly after 11:15 this morning. Thank you all.